This is the Andromeda Galaxy. It is one of over 200 billion galaxies in our universe, and each galaxy is a cluster of about 200 billion stars. But our numerical universe of information is also vast. How can we manage our ever-increasing data and information? Hi, my name is Joe Johnson, and I'm going to present a methodology for how we can manage numerical information in a better way. Numbers serve to discipline rhetoric. Without them, it is too easy to follow flights of fantasy, to ignore the world as it is, and to remold it nearer the heart's desire. This presentation, thus, will center on numerical information rather than on words and text. There is a deep problem that is largely ignored. A number by itself is rather void of meaning and incomplete. Values need the complement of their units of measurement, accuracy level, and defining meaning and descriptors of metadata. But our current data is not tightly attached to these three other properties. The associated units, error level, and exact meaning are scattered, non-standard, and can only be linked by intelligent humans and not computers. Humans must prepare data each time it is used for electronic processing, a process that is error-prone and costly, and which prevents advances in artificial intelligence. But just imagine if every number were tightly bound with its units, accuracy, and meaning in a new object, a MetaNumber object, a universal standard, where both humans and computers could read them without ambiguity, and where every single number had a unique name that could be used mathematically, and units and errors were automatically computed, and every calculation gave a resulting MetaNumber that could be called up and reused. Then computers, as well as humans, could instantly read data sets, and artificial intelligence would be transformed to a new level where computers could begin reading on their own. And now that we have designed programs to convert existing digital tables to this new MetaNumber standard, this enables us to take data that already exists and utilize it in the standard format. We devised a means for converting a numerical MetaNumber table then to a network among the rows and another network among the columns. We can then extract hidden information in these two networks in the form of clusters, like galaxies or clusters of stars. We then devised a method to link these clusters into a vast supernet spanning all numerical information, a single, unified, connected numerical universe where humans and computers can jointly apply new analytics. I'm going to describe my proposed solution. Now, this presentation will describe this new MetaNumber standard object that links value, units, error, and meaning, and also describe the automatic processing of the MetaNumber components into other MetaNumbers with numerical results, full dimensional and error analysis, and tracking of all associated defining metadata. One critical requirement is that both computers and humans can easily read these MetaNumber objects. Here are some of our requirements. Our foundation is the International Scientific, IS, or metric system. It must allow for unlimited descriptive and defining metadata and tags without slowing the processing. It must encompass existing naming standards and support collaborative work, and must also utilize existing standards in computer science and the traditional scientific, commercial, and normal usage. It must track all computational paths and allow extensions of both the SI foundational units and for user-defined units. One must be able to call the computational MetaNumber engine from a user's existing software using API calls. and the results of all calculations must be expressed either in the metric default or any other valid user units. Okay, let me describe first numerical accuracy. Let's first address the means for attaching numerical accuracy, which is often called numerical uncertainty. Such accuracy is critical in all engineering, manufacturing, commerce, weather modeling, and in fact every area where numbers are used. The program treats a value as exact if it has no expressed decimal point. Now, such a decimal point can always be removed using the scientific notation in these examples. For example, you'll see here that we have a decimal point and it's been converted by shifting the exponent to a form in scientific notation where there is no decimal point, and this will be treated as exact. If the decimal point is present, then the system encodes the error depending upon the number of significant digits and converts this value to something called a U-float, a new kind of object. Now notice how the decimal results in this conversion to the U-float appear. Here we have the decimal, and when it's processed by the computer, it's in this form right here, which shows the error. Our system keeps all of the 700 internal constants and unit conversions as exact. But consider these examples. Here we add 4 plus 5. There are no decimals, so we get an exact 9. But if we add 4.0 to 5, then we get 9.00 with an error showing exactly where the error is. And that error arises from the fact that this 5 here does not have another digit here. Even though it's treated as exact, it's added to a number that's not exact. Here's a number that's treated as exact and exact, and we get an exact answer. But if we wrote this in the form with the decimal point, then we would get the associated error. So if the uncertainty value is not needed, ignore it. Use the value, but remember the value as listed represents the result. Now let's look at how we encode units. Units are used just like mathematical variables and can be mixed in any valid way. Here you see the kilogram added to so many pounds. And the result comes out because of the decimals with some error. Units are always single names. We use ounce troy, not troy space ounce. And here's 4 times troy ounce, and you'll notice that's exact because there was no decimal point here. We always use lowercase, which is the custom and standard in all of computer science. 0 to 9 characters and an interior underscore. So for example, we have units that are called mile, Mach, this is speed of sound, speed of light, C, cubic meters, 1 over second squared, written this way, that's where this implies a minus sign, a gallon. We use Kelvin or K, but not with a capital. We use ampere, amp, or A, but not a capital ampere. No information is allowed to be in any font, superscripts, or subscripts. So we cannot write in MetaNumber M with a square here, but we can write M2. We can not write S to the minus 2, but S underscore 2. To continue our designation of units, we do not allow Greek or any other alphabetic or special symbols. For example, we must type ohm, O-H-M, in lowercase, not a Greek letter omega. HV for H-var in quantum theory, not H with a slash through it. PI, not the symbol pi. With a few exceptions, we use only the singular spelling and not the plural. Foot and not feet, mile and not miles, gallon and not gallons. One of the reasons for that is there's so many ways to do the plurals, there would be misspellings that would be resulting from that. So all are defined in terms of the basic SI units, which are the meter, the kilogram, the second, the ampere, the Kelvin, and the candela, or abbreviated as M, kg, S, A, K, and CD. So you can use either these names or these abbreviations. The prefixes are treated as separate words that can be attached and compounded as needed in any mathematically valid order. So, for example, we can write micro thousand nano dozen feet, and that will come out automatically correctly. It'll allow metric, English, and other common dimensionless prefixes like thousand and so forth, million, billion, quadrillion. All results are given in SI, Scientific International, or metric units by default. So if we take 4 meters times 8 meters, we get 32 square meters. However, if we want any other units that we desire, we can write it in the form expression exclamation point units desired. We could take, for example, 4 times meter plus 8 times meter, provide the answer in acre, and it gives us the exact answer in acres. Or look at the speed of light in miles per week, which gives us this answer here. If you make a dimensional mistake, it will be trapped and give you an error. The results that you compute are sequentially numbered for every user, and you are able to achieve getting all past user results. The past results cannot be erased as they might be used in future expressions. We can get the past result number 18 either by writing history 18 or my underscore 18 in square brackets. So we can say 2 times my 18, and that becomes a variable, so we can use any result like this from the past into new expressions in the future. The users can reuse their past results with this format, and our user's history file can be viewed and even copied and downloaded for other use. If we write history 153 space 20, this exact expression here, it'll begin with the 20th value and provide 153 values in the output, which you can then copy. If the history number offset is missing, then 10 will be the default. Now, behind the scenes, past results are stored in a table with the variables as shown. So what we do in the background is we have a database that stores username, the sequence number, the date time of the computation, the input string, the result, the unit's ID, which is a code for the exact unit structure, and the subject. There's an optional subject that we can set by saying subject equals any name. We also have some optional base units that can be used or not used. There are 6 of these that are available. They are the bit, which can be used as bit or B, a binary bit of information, which is a 1, 0 or true, false, used in information theory like the flop or op, which is 1 unit, a floating point operation. A person, or P, which is a unit of a living human. A dollar, USD, or D, which is the US dollar for the time which it was put in, and the value does change. BN, which is baryon number, which is conserved like charge. And LN, which is the lepton number, which is like an electron. And these are also conserved like charge. This allows us some very extensive types of new units to track. We can look at population density, for example, 45.2 persons per hectare. We can look at income, as this many thousands, $34,000 per person per year. We can look at information flow rates, or like the internet, as gigabits per second, or processing speed in teraflops, where flops are equal to a flop per second, or a floating point operation per second. Any metadata can be attached to any number using the expression number times any metadata in brackets. You see these brackets right here? We can put any structure in here we want to. The expression anything at all always evaluates to 1. So the program looks at these braces, and anything that's inside, it throws the whole thing away, makes it equal to 1, So when we multiply by it, like right here, when we say multiply by this, we're really multiplying by 1, but it gives us a container for the information that's attached to the MetaNumber. In particular, we can use bracket dot or dot slash reason equals by division by 0 to indicate a missing value. We can even have questionable data, which is indicated this way, and you can even put in, if you wish, a reason why it's questionable. A user can set the subject by saying, as we mentioned a minute ago, subject equals a value that we set equal to that subject, or we can say subject equals to remove the subject, or subject equals question mark to determine what the current subject is. Let's consider metadata more extensively. There's some the metadata we just described applied to a single number, and it's attached to it. But sometimes we have metadata that applies to every metanumber in a row or a column, and it can be placed in that row or column, such as a web link. Rows or columns that contain names that begin with a % contain associated metadata and not metanumbers. So if we had a column or a row with a %, everything in that column becomes a heading for metadata. For example, we might have % name, and that means this is a % here, so everything here is actually metadata. You'll notice here we're saying this is a symbol. We're going to put symbols down here. Density occurs here, atomic weights here, and so forth. The double % means that this is actually a unique keyword in this column that can be used as an index. For example, in the elements table, we'll see that these are the names of the elements, hydrogen, helium, and so forth. And the symbol is actually also unique, which would be H or HE. Here we show a web link for the symbol, for the densities, where we get the atomic weights. The next column would be this name, hydrogen. The symbol is H. The density is given here, and the atomic weight is over here. You'll notice that the units are attached. There are decimals here, so these will be treated as uncertain values. Here's helium with the symbol HE, which is also unique because it has a double % here. So this is a unique name for this row of metadata, and there's no % here, so this row is metadata, and there's no % here, so this is actually a metanumber that's occurring here and here. If there's a % here, it means everything in this column is metadata, not a number. And if there's a % here, it's metadata and not a metanumber. It's not an actual value. And let's look at archive values. What we need to do is we need to store data in tables on the default server in a form where we can retrieve them. The table dimension can be 0 for one number, 1 for a column of numbers, 2 for a normal type of table where we have entities versus properties in rows and columns. The table, row, and column must have unique names, we call indices, for these metanumber values. And a value is accessed in a two-dimensional table as a table name, underscore, row name, underscore, column name. Now, if this is only one-dimensional, this will be absent, and we'll have table name and row name. This gives a unique path to indicate the exact location of the metanumber, because we only have in the default server and default directory one unique table name. Thus, each archived metanumber value has a unique name. For example, E, gold, thermal conductivity, will give us the thermal conductivity of gold from the elements table. If metanumbers are stored at any location other than the default server, then they're indicated by the internet path and the directory path and then actually a double underscore, and then the table name, row name, and column name. This allows a totally unique path to uniquely name every metanumber, so every number has a unique name. Those names which are in the brackets can be used in any mathematical expression. Let me give you an example. We could take bracket E lead density and divide by E gold density, and that would give the density ratio of this number here, and you'll notice there are no units because it's a dimensionless ratio. Documentation. Well, one can enter any information that we want with a number sign in the first position that we type and make that any string, and that is not processed but is kept as a comment. You could almost, if you save these comment strings for what you're doing in your computation, they're saved with the sequence number, so you can print all of this out and can almost write a book. So by documenting one's work with this number sign or hash sign, it will explain the process that you're using, and you can archive your data that way. Thus, you can actually compose a document that only needs minor editing or formatting. Let me give you some sample problems. We could have an expression, exclamation point, units desired, and it shows how the result is given in what we want. We have 16 feet plus 38 inches minus 1.2 times meter, and you have to have the multiplication or division signs here. Then we put exclamation point feet, and it gives us the number of feet, and you'll notice the associated accuracy level and uncertainty. Metric prefixes, as I mentioned before, can be used in any order. So we could have 456 times billion times kilo times dozen times giga times million, and it'll give us this number right here. Now here's a very practical problem. We have a farmer, and he has 382.6 acres, and he needs 1.8 inches of rain. How many gallons would this be? Well, you know that that's quite a hard calculation, doing all that conversion. Here you simply write 38.26 times acre times 1.8 times inch, and that's area times height. And then say, give that to me in gallons. There it is in gallons with the associated accuracy. You simply multiply the area times the height, and the units are automatically managed. Here's some other sample problems. First, I want you to notice that we have mixed units here. We look for the gravitational attraction between 222.3 pound man and an 85.1 kilogram golf cart that's 6 feet away. So we've mixed metric and English units. Well, we use the equation force equals the universal gravitational constant times the first mass times the second divided by the distance squared to get the force in newtons. And you'll see here that capital G is, we always use small g, lowercase always. So the answer is G times 222.3 times pound times 85.1 times kilogram divided by the 6 feet squared, and it gives you the force in newtons. Another one that's kind of hard to work is a sports car. It goes from 0 to 60 miles an hour in 2.1 seconds. How many G's would that be? I need to tell you that AG is the acceleration due to gravity in this program. And all you have to do is say it goes 60 miles per hour minus 0 divided by the time. That gives us an acceleration velocity divided by time. And you put exclamation point AG, and it tells you it's 1.3 G's of gravity, or accelerations due to gravity. Well, you can find MetaNumber at this site, www.metanumber.com. And we have, the website has instructions, videos, technical papers, simple examples that can be used by someone even in grammar school. We show expression calculations. We show how to get to the APIs to link your MetaNumber code, your code, personal code, to MetaNumber to run it. as part of your code. We have standardized tables that you can look for, and we're in the process of adding more and more of those all the time. We have an automated network and cluster analysis program of MetaNumber tables, and we don't have a SuperNet yet. I'll describe these later. And we show, I like to say, our appreciation to the Office of the University of South Carolina Vice President of Research for our Aspire 1 and Aspire 2 supporting grants. The faculty co-PIs in Phase 1 are the following people, and you see we've had a very extensive staff helping us. And in Phase 2, we have these people that have helped us. And then the student associates in both Phase 1 and Phase 2 are listed here. This slide presentation is on the web also, so you can go back and look at it more slowly, or look at it with the typed notes at the bottom. And I thank you for your interest. I suggest you go see metanumber.com, or you can look at our website and look under MetaNumber for all types of resources. And also, you know, things change over time, so you visit here to get the latest in functions and operations and naming convention. This is how you may contact me. And we are making 2 more videos, one on MetaNumber networks and the cluster analysis, and also one that's a more technical PowerPoint that shows how that cluster analysis can be done and what the mathematics behind it having to do with Lie groups and Lie algebras and Markov theory. Thank you very much.